Alright, so in this particular video, we have two balls, M1, initially moving in the southeast direction here with a speed of 0.9, and then ball 2 is moving perfectly to the right or eastward here at a speed of 0.54, and then after they collide, ball 1 is going to ricochet off and go off into the first quadrant northeast, and then ball 2 is going to move in the southeast quadrant here. It asks us to find VF1, so to find the final velocity of ball 1, we need to find a couple pieces of information. We need to find VF1x and then VF1y. Alright, so let's go ahead and crack it up. In order to do so, set up conservation linear momentum in the x direction by itself, in the y direction by itself. I'm just going to start with the x here. And I'm just going to label everything that I know in the x direction from the initial to the final frame. So if you look at this particular diagram, M2 is already moving in the x direction, so we don't have to do anything fancy for the x direction here. However, M1 is pointing in the southeast direction, so therefore it has to have a V0 or V not 1x here. Okay. The angle here is 40 because the angle given in the diagram touches the vertical axis, which I don't mind. So if this is 50 degrees, I like using the angle that touches the horizontal axis, which is 40 because it has to add up to 90. Other than that, I'm just going to go ahead and find V not 1x. V not 1x simply V not 1 times cosine of the angle, cosine being 40 here. This is cosine of 40 degrees. Okay. If you want to stick with the 50 degrees given, then you would just do sine of 50. That's up to you. All right. Other than that, I already know what V not 1x is. It would just be the hypotenuse, which is 0.9 times cosine of 40, which would just be some number. And then as you can see here on the right side though, I have ball 1 moving in the northeast, so it has to have a horizontal velocity pointing right. And then ball 2 is moving in the southeast, which I can find the horizontal component really quick here as well. All right, using the same strategy, I can just go ahead and say that VF2x here would just be the hypotenuse, which is given as 0.7, and then times cosine of 35. This angle here is 35, which is touching the x-axis, and then VF2x here is also touching the x-axis, so the angle here would be identical, which is also 35. Okay, I didn't label it for you just because these are two parallel lines, so it is cut by a diagonal, which suggests that this is 35. Where my cursor is right now, that's also 35. All right. The only thing I'm missing here is VF1x, so that's what I need to find. So if I set up my conservation linear momentum in the x direction, I will eventually find VF1x here. Okay. All right. So in my statement here, I have two objects in this moving in the x direction, and then in the final frame, I also have two objects moving in the northeast and then in the southeast, but both of these objects have the east component. Okay. So here I have it labeled as M1 VF1x. Plus M2 VF2x. I'm adding because both of these are moving to the right of the screen. All right. Other than that, I'm just going to plug in values. M1 is given as 0.15 kilograms. V not 1x here, which I showed earlier is 0.9 times cosine of 40. That's what I substituted in for. M2 here is 0.26, which is given. And then M not 2x. If you plug this in, it's given to us here as 0.54. Okay, so even though the diagram here just calls it V not 2, really V not 2, which is the same as V not 2x because it's already pointing in the x direction. So that 0.54 is given. And one on the right is 0.15 VF1x. I don't know. As a matter of fact, that's one of the components I actually need to find in order to solve this problem. And then M2 is given as 0.26, and then VF2x is 0.7 cosine of 35, and is also positive because if you look at ball 2 in the fourth quadrant here in the southeast direction here, VF2x is 0.7, which is hypotenuse times cosine of 35. Okay, I'm just going to clean up this a little bit. 0.15 times 0.9 times cosine of 40 will give you about 0.1034. 0.26 times 0.54 will give you about 0.1404. And then on the right here, 0.26 times 0.7 times cosine of 35 on your calculator reduces down to about 0.1491. So I'm just going to combine the left two terms here because these are like terms, and then that'll give you about 0.2438. And then on the right side, I haven't done anything. So here I have 0.2438 and then 0.1491. These are like terms. So I'm going to go ahead and subtract 0.1491 from both sides just to get VF1x by itself. So that's where this number comes from. 0.0947 comes from taking 2438 minus 1491. At this point, as you can see, to get VF1x by itself, just divide both sides by 0.15. So if you do that properly in your calculator, you should get about 0.6313. Okay. So that is VF1X. So I'm just going to go ahead and label this in my diagram. So this is VF1X because it's pointing to the right. And that value I just calculated to be 0.6313. Well, I can't do anything yet because I don't know what the angle is. I only have one leg. So to find the hypotenuse, which is VF1 here, I need more information, okay? But the angle is not given, so I need to find VF2Y. So therefore, I'm just going to use the same strategy, but in the Y direction here. So I'm going to say initial momentum in the Y direction equals the final momentum in the Y direction. And then as you can see, if you look at this particular diagram where my arrow just came up, the only ball that has a Y component initially is M1 because M1 is moving in the southeast. So its horizontal component is pointing right, but its vertical component is actually pointing down. And then if you look on the right side here, okay. Oh, by the way, this hopefully you kept up with the V1 not X. Therefore, I'm using the same strategy here. V not 1 Y is the same thing except it's sine because I'm using the angle that touches the X-axis. Okay. And then on the right side here, VF2 is in the southeast quadrant, so therefore its vertical component is pointing down the page, which is negative. And then we can use the same geometry skill. So I can say VF2Y is the hypotenuse, which is 0.7 times sine of 35 because it is the opposite leg of this angle that I'm tracing back and forth with my cursor there. So if you look across, that's your opposite. Opposite in this case would be sine because I'm using the angle that touches the x-axis, okay? All right, so really the only thing we're missing here is just VF1Y. So if I set this up, here I highlight the negative sign for you because initially, once again, M1 is moving right and down. Okay, so the initial momentum here is in the downward direction or negative direction. So I'm going to go ahead and introduce my negative sign there. And then if you look at M1 here, M1 is moving in the northeast, north being positive. So I kept M1 V1 Y positive, but then this term here on the right, I'm actually going to go ahead and say that it's negative. You can add a negative, but I'll just go ahead and subtract it. So that's that. Okay. Here I'm just going to plug in values. M1.15, V01 or V01Y is just 0.9 times sine of 40. And likewise on the right side, but you notice here the only thing I don't know is VF1Y, which is what I'm trying to find because then that'll complete my right triangle. And then the negative sign gets carried down. But keep in mind that here, I'm just going to go ahead and plug in 0.6 as the mass. But for VF2Y, I want to just plug in 0.7 sine 35 because I've already set that as negative from the get-go, okay? So I took care of the negative sign already. So do not plug in another negative sign here. Otherwise, you'll make it positive, which makes no sense. Using common sense, this is in the north, which is pointing up, east direction. This is in the southeast direction, so the signs must be opposite. All right, simplifying the left side gives us negative 0.0868, and then 0.26 times 0.7 times sine 35 will give you about 0.1044. And then to get VF1Y by itself, simply add this 0.1044 to the left side. So if you add it, you'll get, okay, 0.0176. And then to get VF1Y by itself, divide both sides by 0.15. And then VF1Y is 0.1173. Well, now we just found these two legs right here, right? We already found VF1X, which is 0.6313. And then now we just found VF1Y. We found the vertical component of the velocity there. So that'll be 0.1173. Now that we know the two legs of this right triangle, we can just apply Pythagorean theorem. So therefore, we can say that VF1 square, which is Pythagorean theorem, equals to the x square plus y square. Okay. And that right side simplifies down to 0.4123. And then to get VF1 by itself, we square root both sides. So the square root of 0.4123 is going to give you a magnitude of about 0.642 meters per second. But this is just a speed, right? The question asks you to find the final velocity. So velocity has to have a magnitude or speed and a direction. So this is a two-dimensional problem, so the direction will have to be the angle. So here, in order to find the angle, I'm just going to do tangent of VF1Y over VF1X. So essentially rise over run. My rise being my y component, my run being my horizontal component. You can use sine, cosine if you want. I just like tangent because I already have the information here in my diagram. So once again, I have the opposite leg and the adjacent leg. So I'm just going to go ahead and use tangent because theta here is touching the x-axis. All right. So if I do inverse tan of that, VF1Y, I just pull it from the diagram, which is 0.1173 that I calculated. And then likewise with F1x, that's also from my calculation, which is 0.6313 calculator time. That will give you an angle of about 10.6 degrees. So we would say that the final velocity is 0.642 meters per second, 10.6 degrees northeast, or 10.6 degrees above the positive x-axis in this particular collision. Okay, so that is your answer for this particular video. All right, I hope you see the setup, and hopefully you're careful with your signs and stay nerdy. Don't be whack.